All right. Couple of things. I want to look at the calendar again real quick because it's been about a week since I saw you all. Today is Wednesday, April 3rd. Bless you. There is no lab at all this week. None. Because Monday did not exist. We do have normal class for the foreseeable future. But I want to, again, briefly point out a couple of lab things moving forward, because next week won't have a normal lab, because Monday is Eclipse Day, and I'm very excited about that. I mentioned before that on that day I'm going to do an entire eclipse lecture, basically talking about gravitation and orbit and all that good stuff. And that afternoon will be the eclipse, the afternoon of Monday the 8th. I think the sun should start being blotted out around 1:30 that afternoon. We will reach the maximum totality for this area around 3 or 3:30. It'll only be about 75% totality, but it'll still be pretty cool, and the sky will be visibly a lot darker. And then it'll go back to normal around 4:30. Given that the eclipse is happening that afternoon, I am canceling normal in-person lab for the week because I want people to be able to experience the eclipse if they want to. And similarly to that, as a reminder, you should never look at neither the sun nor the eclipse with your bare eyes. Instead, you should look at them with these. These are eclipse glasses that I got for the whole class.
Yes, sir.
You know that?
It's like that, right?
Yes. And in fact, during the eclipse, the radiation is different and it can hurt you quicker. So, in order to view the eclipse, you should grab a pair of these. They are eclipse glasses and they block out 99.9% of all light. You know that they work because you can look at the projector and see only a pinprick of where the light bulb is. You can come grab a pair of these. I'm going to leave them out on this desk all week. So if you want to watch the eclipse, which I encourage you to do, these things don't happen super often. The fact that there was one about 6 years ago and we're getting another one this quickly is kind of an anomaly.
7.
7? Thank you. I'd already forgotten somehow. Brain.
It's a prophecy, bro.
If you want to grab it, grab a pair, please do. Try to only grabbing one pair for now to make sure that every student in all my sections can get a pair. And then on Monday, if there's extras left, you guys can grab some extras if you want. But Monday's Eclipse Day, and I'm excited if you couldn't tell. Instead of a normal in-person lab next week, I'll give an out-of-class assignment that you guys can work on over the period of the week. It'll be a very short one, just kind of reviewing the eclipse and gravity and orbit-related concepts that we will cover next Monday on the day of. And then the week after that, there will also not be a normal lab because we will be having test 2 that week. Test 2 will take place during lab time, the 15th, the 16th, and the 17th. We will take in-class time leading up to it and during those days to make sure everyone is comfortable with the test before it happens, like with test 1. And then the last actual normal lab of the semester will be the last week of full classes, the 22nd, the 23rd, and the 24th. I'm planning electricity and circuits for that week. Yes? Finals start April 29th, the week after that.
When is our finals due for this class?
That is an excellent question, and that's something I should probably start keeping on the board. I have 2 lectures of this course, so there are 2 pre-assigned. Did I actually remember to save the academic calendar? That is unprecedented for me. Exam schedules. Final exams. Oh. There we go. Okay, spring 2024. My 2 lecture sections for this class are E and F, meaning the 2 regularly scheduled exam times for this course are Monday, April 29th, one at 8:30 a.m. and another at 1:30 p.m. Now, brain. Similar to the tests where I'm giving the same test during every possible section that is being proctored, I'm giving the same exam during both time slots. Therefore, I don't really care which one you show up for. Technically, this is the F section, so technically, the 1:30 time slot is yours, but if you prefer the 8:30 for any reason, you are allowed to simply show up then instead. And given that various students have various accommodations and scheduling issues, I'm open to creating more time slots than just these two that the school has scheduled. Like, if I'm gonna be here another day proctoring for another group of students at a different time, I will probably, if needed, create extra sections if needed. At this time, none of those are scheduled yet though, so these are the two guaranteed ones that you can bank on being able to attend. Does that answer the question?
Yeah.
Okay. That was a lot of calendar stuff. How y'all feeling? Okay. As a reminder, that is still a month out. I'm gonna make sure everyone's ready for it. I do exam prep stuff like I do test review stuff. Any questions before we get started on something new today? All right. Today, we start looking at some new concepts, that being waves and eventually sound. I'll talk a little bit about light as well, but sound, general wave mechanics, and then sound mechanics will be the things we focus on. Again, we're kind of jumping around in the chapters that the book is based on, so I base the chapter numbers on the source book if you are using a personal copy of it. This would be what the book calls chapter 19. So again, kind of skipping around a bit. Sorry if this numbering system is confusing. And our goal is to be looking at the behaviors of all general waves, and then we'll look at, additionally, a couple specific things for a few specific types, namely sound. Now, as per usual, I like to define what it is we're discussing. And before I can define waves, I actually have to define what waves are made of. So before defining waves, I first have to define vibrations, because a wave is just a traveling vibration. So, what are vibrations? The physics definition of a vibration is that they are a simple harmonic oscillation. And oscillation is a very fancy word for a constant repeated motion back and forth between 2 points. As an example, this mass and spring that I have hanging from the front of the room is what is called an oscillator because it's about to start oscillating. This is currently its base condition where it's not oscillating. Note that the mass normally hangs at this particular height, and in this base configuration, there's some energy stored elastically in the spring. The mass itself has some GPE as well because it's able to fall from this height. And I'm going to take that mass, I'm using my right hand here to indicate the base height. I'm going to take that mass, pull the spring down from that base height, and release it. And now the mass is oscillating at 2 different fixed points, between 2 different fixed points, back and forth from that base configuration. So again, this hand is the base height, and then what the mass is currently doing is oscillating between 2 extremes around that base height. That is the basic definition of all oscillation, and therefore all vibrations. And basically anything that is doing the same motion constantly back and forth between 2 points can be classified as an oscillator, and therefore it exhibits wave-like behaviors. Pendulums are another good example of this, because a pendulum, all it does is it moves back and forth between 2 fixed points. We got the starting point here, we have the other side, and the back. So technically speaking, this is on some level exactly the same as that. They exhibit the same wave behaviors. But again, anything that is capable of vibrating or oscillating does this basic thing. And that includes shattering a wine glass with sound, if you're familiar with this trick. If you sing very loudly at the correct frequency, the resonant frequency of glass, you can make the glass start vibrating. Notice that it too is flexing between two extremes. You've got the base configuration, where the glass is normal, and the two extremes it's flexing between are flexing outward in this axis, and then separately outward in this axis. And if you keep singing at it at the correct frequency, that vibration just gets bigger and stronger, eventually flexing so far in one direction that it can't bear it and it just shatters. All of these, mathematically speaking, are the same basic concept, oscillating between around a base point to two different extremes. And that's all a vibration is. Sound all right so far? All right. Now, because physicists love measuring things and putting numbers on things, I want to first look at the various aspects of vibration and oscillation behavior that we are capable of measuring, that we will be measuring. So these first three things are three aspects of vibrations that we measure in physics. The first of those things you can measure is the amplitude of a particular oscillation. Amplitude is basically how big is the vibration, how far from baseline is it currently being deformed. Again, in reference to this one that I've got right here, my right hand here is the base configuration before I move it. I then pull it down by, maybe 3 centimeters, and then it oscillates up and down between 3 centimeters below the base position, and 3 centimeters above the base position. That 3 centimeters is the amplitude. It's the distance from baseline to either extreme. The amplitude is not the distance from top to bottom. I want to make that clear. If that is representing the oscillation over time, the dotted line here is the baseline. That is an amplitude measurement from baseline to the topmost point, or that is an amplitude measurement from baseline to the lowest most point. Amplitude is not from lowest to highest. I want to make that clear. Make sense? Amplitude is the strength of the deformation, not the distance from highest to lowest. But it is technically just a very specific distance measurement. So we still measure it in meters. It's just a specific word for a specific distance measurement.
So is the distance from like here to here instead of here to here, or the other way around?
Well, it kind of depends on the object. I'm going to try to demonstrate something I'm going to show later. Use a different coil. Using this as a different oscillator, if I note the coil that I'm pinching right now, if I pull it 1 centimeter up, oof, I gotta hold on to that piece. Okay, resetting. Note the coil that I'm currently holding. If I pull this coil 1 centimeter upwards from its baseline, the amplitude of that vibration is 1 centimeter either up or down. If instead of up and down, I strum it side to side, so say this is baseline and I pull it 1 centimeter this way, that amplitude is still 1 centimeter. The wave just looks a little bit different, but it's still 1 centimeter amplitude. Does that answer the question?
Yeah.
Yeah. It's capable of either direction. It doesn't have to be up or down. It's from base to either extreme, regardless of which axis it's in. if I took it off of the sync. That is the first thing about vibrations and oscillations that you can measure, basically just how big they are. Next is the frequency of an oscillation. The mathematical measurement of frequency is really just how frequently something takes place. The way you calculate frequency is you determine how many events, full event cycles, take place in 1 second. The unit for frequency is Hertz, spelled H-E-R-T-Z, after German physicist Heinrich Hertz. And you might have heard frequency and hertz in relation to sound before. Sound familiar? Pun not intended. That is talking about the same thing. The frequency of a sound wave will tell you how many full sound waves strike your eardrum of every single second for that particular frequency. Higher frequency sound means more waves strike your ear every single second. Low frequency sound means less waves strike every single second. It is literally events per second. So the formula for frequency is 1 hertz is defined as 1 event every 1 second. If this oscillator, again, I'll just get it going again, goes through 1 full cycle of bottom to top, back down to bottom, that would be 1 full oscillation, 1 full cycle of motion. 1 full event in 1 second would be a frequency of 1 hertz. If it does it twice in 1 second, 2 events per second, that is 2 hertz, so on and so forth, upwards. High frequency events take place a lot in 1 second. So if anyone is ever talking about something like 10,000 hertz sound waves, that means 10,000 waves strike your eardrum every second. And frequencies only get higher from there, as it turns out. Meanwhile, low frequency means a low number of events every single second. If it takes it 3 seconds for that oscillator to go through 1 full cycle, that's 1 event per 3 seconds, that's only 1/3 of a hertz. So the definition of a hertz is 1 event per 1 second. The full word is abbreviated to just Hz as a unit. And since frequencies do tend to get pretty big, you will often see things like kilohertz or megahertz or gigahertz, depending on what type of wave you're looking at. Light, for example, has frequencies in the megahertz, like all colors of light. Frequency sound okay? Okay. Last vibration mechanic that we can measure for right now is period of oscillation. And this is literally just the opposite of frequency. I think we only gave them 2 different names because they were used by 2 different groups of people at 2 different points in history, because they tell you the same basic information. Frequency is events per second. Period is seconds per event. If I tell you the period of oscillation for this device, that tells you how many seconds it takes to go through 1 full cycle. If this thing's period of oscillation is 1 second, it takes it 1 second to go through 1 full oscillation. If its period of oscillation is 2 seconds, it takes 2 seconds to cycle through 1 full event. Actually, instead of that, I'll try to show that with a pendulum. So that's a period of oscillation of about 2 seconds, 1 second out, 1 second back. And again, 1 full event is always the complete cycle of out and back. So it's not the time to get to here, take that. It's not the time to get to there, it's the time to get there and back. I want to make that clear. This would be about 2 seconds. Meanwhile, that's closer to a period of 1 second. 1 second to get out and back. Make sense? Does that not make sense? Let me ask it like that. Okay. Period of oscillation, since it's just a very specific measurement of time, its variable is uppercase T. It's time, but more specific. And that means it's also still measured in seconds. It doesn't have a unique unit. Main thing I want you to note though is it is literally the inverse of frequency. Frequency is events per second, period is seconds per event. If you know one, you just invert it, one divided by thing, and you get the other. And that tends to mean that if something has a very large frequency, it's going to have a very small period of oscillation, and vice versa. If something has a frequency of 10,000 hertz, that means 10,000 events take place every 1 second. If you take that and calculate period instead, that would be 1 second per 10,000 events, which will be a very tiny number, which we'll demonstrate in a second. Conceptually though, sound okay before we start trying to apply any of this? Okay. Let's use those measurement definitions very briefly. This image is going to try to put some numbers to that oscillator I've got going over there. Let's say that this is the base configuration. I raise it 10 centimeters, not literally, but metaphorically. And it now oscillates between 10 centimeters above baseline to 10 centimeters below baseline and back and forth until it runs out of juice. Visualized here, each picture here is just kind of stepping forwards in time. So top, down to low, back up to top, so on and so forth. And it takes it 2 full seconds to go from top, down, and back again. 2 seconds per one oscillation. Given all of that information, first question, what is the amplitude of this vibration?
Centimeters.
10 centimeters, correct. Why is it not 20 centimeters?
Because it's 10 centimeters up 10 centimeters.
Exactly, very good. It's the distance from baseline. It is not the distance from extreme to extreme. It's from baseline to either extreme. So the 10 centimeters is already the amplitude. Very good. Next, given the other part here, what is the frequency of this vibration? Half a hertz. Very good. Keep picking up the phone marker. Better. Frequency is number of events over number of seconds. Therefore, 1 full event over 2 seconds is half a hertz. Small frequency means the event does not happen very frequently. Big frequency means it happens very frequently. That's how I remember it anyway. So that is in fact the frequency. What then is the period of oscillation of this particular vibration?
Two seconds.
2 seconds, very good. Frequency is events over seconds. Meanwhile, period is number of seconds over number of events. Here we have 2 seconds per one event, therefore the period is 2 seconds. Again, they are inverses of one another. 1 over 2 is 1/2. 1 over 1/2 is 2. So something that has a high period of oscillation takes a long time to take place, therefore it will have a very low frequency. Feel all right with the first part? All right. Second separate question, just to drive home the relationship between frequency and period one more time. The pistons inside of a car engine can get so fast that they complete 120 full oscillations in 1 second. If you're unfamiliar with car engines, the way that they tend to work is you have a cylinder with a piston in it. That piston is able to slide in and out. You put a small amount of gasoline inside of the cylinder, you blow it up, and that pushes the cylinder out. Then, combination of pressure and temperature, you draw the cylinder back in, and then you are now reset for the next explosion, and you get that constant motion back and forth. Most engines tend to have a couple of these, and that repeated motion is transferred into the wheel of your car. These pistons go through 120 full cycles in 1 second. Please tell me very quickly, very briefly, what is the frequency and period of oscillation of this repeated motion?
Speed is 120
Yep. And what is the unit on frequency?
hertz.
Very good. 120 events over 1 second. 120 hertz.
The periods would be 0.0083.
Correct. 1 over 120. Oops, I wrote seconds twice.
Seconds.
So, previously, the bigger the period of oscillation, the smaller the frequency. Here we have the inverse. The bigger the frequency, the smaller the period of oscillation. If something has an incredibly high frequency, that means that the period of oscillation will be teeny tiny because it does not take very long for a single one of those events to take place. Again, high frequency sound waves, like 10,000 hertz, you are being bombarded with 10,000 full waves every 1 second. And 10,000 hertz isn't even that high. That's like the upper end of human speaking voice. Well, 10,000 hertz isn't very high for sound. Let me say it like that. But it's minuscule for light. Light frequencies get in the megahertz and stay there. Questions? Wait. Yeah, light is tiny wavelength. All right. Now, those are all things that we use to describe vibrations, and now we are going to, in turn, use them to start talking about waves and how waves work. To that end, I want to point something out about this image before moving on. Did anyone notice that that blue line forms a wave? Not this blue line, but the upper one. This picture is again meant to represent the oscillation over time, so position over time of the yellow ball, basically. And if you track it over time, you get the shape of a sine wave. That being sine spelled S-I-N-E, the math concept that you might remember from geometry. Forgive my handwriting. Sine wave. This is the same as the sine button on your calculator, but your calculator tends to take the E off. This is why we use sine waves to visually represent waves. Waves often take this shape because literally wave motion over time matches the sine function on your calculator. So if something ever calls this a sine wave, that is why. It is referencing, again, the sine function on your calculator. And it is pronounced sine, not sin. So, we define vibrations so that we can now say that waves are traveling vibrations. This oscillator has been very sluggishly oscillating basically in place. It's only ever moving between two fixed points. It's not really going anywhere other than those two fixed points. And whenever you have a vibration or an oscillation, this process involves a constant transferring and transforming of energy. If you recall from energy and work a month or two ago, anytime something is moving and exerting forces, there's going to be an energy use and transfer and transformation. And this process, energy is constantly cycling between types as this very simple action takes place. As the spring extends and contracts, it acquires EPE, elastic potential energy, and also surrenders it when it goes back to its base shape. It's constantly flexing and compressing, changing its EPE level. The weighted mass is constantly changing its GPE level since it's moving up and down, but it's also changing its KE level because its velocity is constantly changing. This whole process is just a giant festival of energy transferring and transforming between states and parts of the apparatus. Now this vibration, we don't consider this traveling, because even though the object is moving around and the energy is going all over the place, it's still staying in the same region of space. The energy is not leaving this overall system, this overall geographic location. What waves do is they take this vibration and they take all that energy and they send it somewhere else. Waves are just traveling vibrations, and therefore they are traveling energy. Since the vibration itself is constantly transforming energy, the wave takes that energy and sends it along with the traveling vibration. Sound all right so far? Okay. Now this is true of all waves. We're going to look at lots of different types of waves. We'll begin with some visual, very mechanical waves that we can create and see in the room here. On screen right now currently is an image of a spring, very much like this one. Just a spring coil that has a wave traveling through it. I'm going to try to rebuild my setup here and do the same basic thing. So here we have a spring coil, both on screen and also here with the physical spring. When I cause a part of the spring to vibrate, that vibration and the energy of that vibration is able to travel from point A to point B and then likely bounce back and forth several times. So I'm just going to pluck one coil of this spring, and the motion, therefore the energy, is zooming from one end and then back and forth until it runs out of steam because of friction. Again, the vibration is what's going back and forth, and therefore the energy is what's going back and forth. All waves do this, even if they are not made of slinkies. Sound does this. It's just instead of traveling through slinky, sound travels through air. In reference to that, most waves travel through some sort of a medium. That's just the technical term for the substance that the wave travels through. Since waves travel, we call the medium the thing that they are currently traveling through. Again, this spring is the medium for the waves traveling through the spring. If the spring wasn't there, this motion wouldn't cause any waves to travel. Like I grab air, I pluck air, but there's no spring for the wave to travel through. The spring has to be here for the energy to actually get from point A to point B. So the spring is the medium for that wave, and air is the medium for sound. If you don't have air, you don't have sound, and that's why you can't hear in space. If you've noticed that in movies. Now, technically then, in Star Wars and Star Trek, you shouldn't be hearing the music and the explosions, but they edit those in anyway because it's just kind of weird to see a boom and not hear a boom. But in space, you wouldn't hear the explosion. which is good, because if you could hear in space, the sun would be very loud. It's a constant roaring fire. Anyway, most waves have a medium. That's just the thing that it travels through. The ocean waves have the medium of ocean. Earthquakes have the medium of earth. Earthquakes are waves, if you didn't know that. Sound all right so far? All right. One more detail about this I want to point out. The medium does not travel with the wave. Waves are traveling vibrations, and therefore waves are traveling energy. The energy goes from point A to point B, but the medium itself doesn't go with it. In this picture here, that hand is highlighting a specific coil on this spring. Note that that coil does oscillate as the wave travels through that particular part of the spring, but that coil doesn't go with the energy. This particular wave is traveling from left to right. That means the energy is going from the left side to the right side, and the spring only vibrates when the energy travels through a particular part of it. This coil here starts shaking when the energy travels through that coil, but that coil then returns to its base state once the energy's gone, and it doesn't go further to the right with the energy. It goes back to normal. The material doesn't go with the wave. It just acts as a medium, vibrates in place for a second, and then the energy leaves and the material goes back to normal. I can do the same thing here with this spring coil. Note which coil I'm grabbing here, this coil right here, and if I strum it, energy will shoot back and forth between both sides, but that coil is still in this same basic region of space. The coil didn't rip off from the sink and go that way. I can even show the same thing will happen if I strum in a different axis. So instead of plucking upwards, I'm now going to pluck rightwards from your angle. Again, coil's still here. It'll shake when the energy is present in this spot, but it doesn't go with the energy all the way to the other end. I wanted to point that out to notice a few things about various types of waves in the world that you've experienced. Most appropriately, sound waves. Sound travels through air, and the air doesn't go with the wave. If air traveled with waves, then every time you spoke, you'd create a gale force wind because the air would go with the sound that you're projecting outwards. Instead, the air just kind of ripples for a second as the energy moves through that particular part of the atmosphere. Literally like a ripple in water. You throw a rock into a pond, the ripple travels outwards from the origin point, but it doesn't bring all the water with it. The water just, for a brief moment, and then it goes back to what it was already doing. Same is true in the ocean, by the way. Ocean waves don't haul the entire ocean to shore with them, barring tidal waves, which have their own weird phenomenon. Generally speaking, an ocean wave, the energy travels to the coast, and then that energy just kind of churns up the water that's already there. Does that make sense? It's why you in a wave pool don't get blasted back with the wave. You just kind of bob up and down, slowly drifting in one direction. Anyway, waves are kind of complicated. I just want to make sure you knew the energy is what's traveling, the medium is not. Have I made that point, I hope? Okay. I'm going to uncoil this before it springs off on its own. Now, since waves are made of traveling vibrations, all the same vocab words from a second ago about vibrations still apply to waves. Waves have amplitude, waves have frequency, waves have periods of oscillation. As they apply to waves, a wave's amplitude would represent the maximum height that the medium rises to from baseline, or alternatively sinks to below baseline. And so technically, when an ocean wave happens, what it does is you start at baseline, you get brought upwards, and you get brought downwards below baseline, and then you settle back at baseline. So, waves do that too. Frequency of a wave will tell you how many full waves travel through a particular area in a given second. Again, 10,000 hertz sound is 10,000 sound waves striking your eardrum every second. And the period of a wave would tell you the time it takes for a single wave to travel and strike something. So high frequency would be the waves happen in a very small amount of time. So all those vocab words still apply. Some words that are specific to waves. So some new variables that we'll be using as we continue talking about waves. First, I want to point out the crests and troughs of the waveform. Crests refers to the high points, troughs refers to the low points. That's just a term that I might use from time to time. So the crests are one amplitude up, they are the peaks. The troughs are one amplitude down, those are the valleys. You could alternately call them peaks and valleys, and that is equally fine. But if you hear crests and troughs, that's what that means. So just a part of the wave structure. Next, something that waves have that vibrations don't is wavelength. You might have heard this in relation to sound or light as well. The wavelength of a wave is literally the length of a wave, the physical length from start to finish of one full vibration. Since they are traveling, they cover distance with time. And the wavelength is the distance the wave covers as it goes through one full cycle, one full oscillation from crest down to trough and back up to crest. So in the case of this particular picture here, if this is a wave that is traveling, and this here is our origin point starting at this crest, the wave travels 5.2 centimeters as it goes from crest down to trough. It would take another 5.2 centimeters to go from trough back up to crest. And so the distance from here to here is the physical length of one entire wave. Because one wave, one full oscillation is one cycle from start to finish. So if you physically put a tape measure at the crest of a wave and measure the distance to the next crest, that is the length of one full wave, that is the wavelength. So the wavelength of this should be 10.4 centimeters. And again, it is a physical length, kind of like how amplitude is also just a specific length measurement. So it's still measured in meters. It's just a very specific distance. But because it's specific, it does have its own variable, that being lambda. That is a lowercase Greek lambda. It's basically just a mirrored and rotated letter Y. I always have to check that one because that's like one of the least commonly used Greek letters in my experience. Oh, at least commonly used in English. Now, additionally, waves travel, so not only do they have length and cover distance, they have velocity. If they're traveling, if they're moving, the wave speed, the wave velocity tells you how fast they are moving, how fast they get from point A to point B. All waves have some velocity, some wave speed, and often the speed of a wave can help you figure out what kind of wave it is, because most wave types have a certain constant speed. You might have heard speed of sound or speed of light, for instance. All sound waves, barring air temperature and air pressure, travel at about the same speed, and all light waves travel at the same speed. So wave type often helps you determine what the speed of that wave should be, and that's going to be one of the things we explore in the coming days. But as measurable concepts, how are we feeling? All right. Last thing I'll point out for today, so that we can start applying it next time, there's a certain specific relationship between wave speed, wave frequency, and wave length that is summarized by this formula. It's one of the things we'll do on Friday. So just setting the board for next time. Wave frequency tells you how many full waves pass a certain point every second. So it's waves per second. Wavelength is the length of one single wave. Therefore, when you take wave frequency and multiply it by wavelength, you've got marker. Where's the marker I was using? I should just keep all the dead lint in the sink. V equals frequency times lambda. Frequency is number of waves in 1 second. And wavelength is length of one wave. When you multiply number of waves by the length of one wave, you get the distance those waves travel over 1 second. And so that is why these two things multiply together to determine wave velocity. Literally, the frequency is just telling you the time frame of the waves, and wavelength tells you the distance they cover in that time frame. So you multiply them together, and that's why they form wave speed. And since most types of waves have constant velocity for that type, all sound waves should have the same velocity of sound, 343 approximately. All light waves should have the same speed of light, 3 times 10 to the 8th. Light is the fastest thing in the universe, if you weren't aware. That means that all waves of a specific type have a specific combination of frequency to wavelength. If all sound waves are at the same speed, that means every frequency of sound has a specific wavelength of sound that has to multiply with that frequency to create the same speed. And that is what we'll start exploring next time. As concepts go, how are we feeling for right now? All right. Let me know if you have any questions. Reminder, no lab this week. And a further reminder, make sure to grab some Eclipse glasses ahead of next week's Eclipse. Don't stare at it without these. And, I don't know if you need anything. It's like a wonderful day.